The s orbitals are all spherically symmetric. Thus, contour plots connecting points of equal electron density are spheres for all values of the principal quantum number n. When n equals 1, the electron density decreases steadily with increasing distance from the nucleus. When n equals 2, the electron density goes to 0, then rises again to a new maximum. The spherical shell around the nucleus where the electron density is 0 is called a node. When n equals 3, there are 2 radial nodes. In summary, s orbitals of differing major quantum number have the same spherical shape, but differ in overall size and the number of nodal surfaces. The noble gas elements, which have completed shells of electrons, also have a spherical electron distribution. Helium has 2 electrons in the 1s orbital. Neon has a completed octet of electrons in the n equals 2 shell. Similarly, argon has a completed octet in the n equals 3 shell. The radial electron density corresponds to the probability of finding an electron at a particular distance from the nucleus. We find that for helium, the radial electron density has one maximum at about 3/10 angstrom radius. For neon, however, the radial electron density has 2 maxima, and one rather close to the nucleus, the second much further out. The first maximum is due in large part to the 1s electrons, which are drawn in close to the nucleus. The second maximum is due largely to the electrons with principal quantum number equal to 2. With argon, there are 3 maxima. The first maximum is due largely to the 1s electrons, which are pulled very close to the nucleus of charge plus 18. The second maximum is due largely to electrons with principal quantum number 2. And the third maximum is due largely to electrons with principal quantum number 3. These maxima correspond to Lewis's idea of shells of electrons. However, the shells are diffuse and overlap considerably.